All right, welcome everyone. Today, we're diving into a really powerful way to survey large populations called two-stage sampling. We're going to focus specifically on a method that helps us deal with a super common problem in the real world. What to do when the groups you're sampling from are all different sizes. So here's our game plan. We're going to build this thing from the ground up, starting with the basic idea. Then we'll look at the math behind it, bring it all to life with a simple example, and then really unpack the core concept of sampling weights and a fantastic technique called PPS. Okay, let's jump right in. So what's the big deal about two-stage sampling? What makes it different? Well, it's all about that second step. See, instead of studying an entire group, what we call a primary sampling unit, or PSU for short, we only take a small sample from within that group. And that means we have to estimate that group's total, which, adds this extra layer of uncertainty that we have to learn how to manage. Okay, first up, a really key concept. We're sampling with replacement. Think of it like drawing a name from a hat, reading it, and then putting it right back in. Because of that, the same group, or PSU, can get picked more than once. So we need a way to keep track. We use this variable, QI, to just count how many times each group shows up in our final sample. And of course, if you add up all those Qs, you just get N, your total sample size. Now, here is an absolutely critical rule. Every single time a group gets picked, we have to take a new independent subsample from it. So let's say a certain PSU gets selected 3 times. We don't just reuse our data from the first time. Nope, we have to go in and do 3 separate independent surveys inside that one group. This gives us multiple estimates for that single PSU's total, which we call T hat IJ. All right, with those building blocks in place, we're ready to tackle the formulas. Now, I know these can look a little intimidating at first glance, but really, they're just clever adjustments to the simpler one-stage formulas. They're designed specifically to handle that extra layer of estimation we just talked about. This right here is the Hansen-Hurwitz estimator, and it's our main tool for estimating the total for the whole population. Let's walk through it. That 1 over n out front, that just means we're going to average n different things. The really important part is what's inside the sum. We take our estimated total for a group, Tij, and we divide it by psi I, which is the probability that we picked that group in the first place. This division is the real magic trick. It's what we call an inflation step. If a group was really unlikely to be picked, its data gets a bigger weight. If it was a common group, it gets a smaller one. This is how we correct for the bias from our sampling method. You do that for each of your n selections, average them all up, and that's your best guess for the total. So what's really cool about this slide is just how simple the formula is. And why is it so simple? Because we sampled with replacement. That means each of our n inflated estimates is like an independent piece of evidence. And this formula, well, it's just the standard sample variance that you learned in interest stats. It calculates how much our individual estimates vary around the average, then divides by n. It's a direct, beautiful benefit of sampling with replacement. Now, getting the mean is pretty intuitive, right? It's just the total divided by the count. In survey statistics, we call this a ratio estimator. We take our estimated total that we just calculated, and we divide it by an estimate of the total population size. We have to estimate the count for the same reason we had to estimate the total. We only have a sample, not a full census. And that population size estimator, M hat, it uses the exact same logic we just saw. You inflate the known sizes of the groups you sampled. Okay, I'll admit this formula for the variance of the mean looks pretty intense. But the core idea is actually all about measuring prediction errors. For each group we sampled, we have an observed inflated total. Then, we can create a predicted total, just based on that group's size and our overall average. This formula is just calculating the difference between the observed and the predicted, what statisticians call a residual. It's basically measuring how well a group's size predicts its total, and that tells us how much uncertainty we have in our overall average. Phew, that was a lot of theory, a lot of formulas. Let's make this all concrete with a really simple, intuitive example. This is going to show you just how incredibly powerful this method can be when we're clever about how we choose our sampling probabilities. Okay, imagine our entire universe consists of just 2 puppy homes. We've got Puppy Palace, which is large with 30 puppies, and then there's Dog's Life, a smaller place with only 10. Our goal is simple. Estimate the average number of legs per puppy. So we're going to sample just one home, but the probability of picking it will be proportional to its size. That means Puppy Palace has a 3 out of 4 chance of being picked. Then, whichever home we choose, we'll just take a simple random sample of 2 puppies. All right, let's follow the numbers, and let's assume, every puppy has 4 legs. So, scenario 1, we select Puppy Palace. Our estimate for the total number of legs there is 120. Now, we apply that inflation step. 120 divided by its selection probability of 3/4 gives us 160. Okay, but what if we picked dog's life instead? Well, the estimated total legs there is 40. We inflate that by its selection probability. 40 divided by 1/4 is also 160. And that is the crucial point. No matter which home we sample, our final estimate for the population total is always 160, which means the estimated average is always 4 legs. The variance of this estimator? It's 0. This is a perfect illustration of the ideal scenario. When the thing you're measuring is perfectly proportional to the size measure you used for selection, the design literally cancels out all the variability. It's beautiful. So that puppy example shows what happens in a perfect world, and it really reveals the powerful mechanics that are at play. To understand those mechanics better, we need to unpack the core concept that makes this whole thing work: sampling weights. So the big advantage of sampling with replacement is, as we saw, simplicity. The variance calculation is so straightforward because all the draws are independent. But that comes at a cost. If your population of groups is small, you actually lose efficiency by potentially picking the same one over and over. Think about it. Each time you reselect a group you've already seen, you're not gaining any new information about the variability between the groups. So how do we actually make this correction happen? We use something called sampling weights. You can think of a weight as a number that tells us how many units in the whole population are being represented by this one single unit in our sample. It's the key mechanism that lets us turn a biased, unequal probability sample into a set of perfectly unbiased estimates. In this simpler, one-stage case, the logic is very direct. The weight is just the inverse of the selection probability, scaled by the sample size n. Here's another way to think about it. If a group has a very, very low chance of being picked, any data we get from it is incredibly valuable, so it gets a higher weight to compensate. And since we observe everyone in that group, they all get to share that same weight. Now for a two-stage design. The final weight for an individual is simply the product of two different parts. The first part is that same group level weight we just saw, which accounts for the chance of picking the group itself. The second part is new. It's the weight from within the group, which is the total group size divided by our subsample size. You just multiply those two together, and that gives you the final weight for each person you surveyed. And all of this brings us to the most common and, frankly, the most powerful application of this theory: probability proportional to size sampling, or as we all call it, PPS. This is where we deliberately tie our selection probabilities to a measure of each group's size. And this right here illustrates the pure elegance of PPS. What we do is we define our selection probability, psi I, as the group size mi, divided by the total population size m0. Now watch what happens when we substitute that into our two-stage weight formula. The first stage weight becomes m0 over n times mi. The second stage weight is still mi over mi, and look what happens. The mi terms, the size of the group, they just cancel out completely. It's beautiful. The result of this is profound. If we then make one more simple decision, to sample the exact same number of elements, let's call it m, in every single group we select, then the weight becomes constant for every single observation in our dataset. This creates what's called a self-weighting sample, which makes analysis so much easier. But it also has huge practical advantages. Field interviewers have the same workload in every city they visit, and we know our total sample size before we even start. And, as we saw with the puppies, if the thing you care about is correlated with size, this design is just incredibly statistically efficient. The big takeaway here is that smart design always beats brute force. By deliberately building size information right into our sampling plan using PPS, we create a system that is elegant, efficient, and honestly, just practical. It's technique that corrects for its own biases, which is why it's a cornerstone of major surveys all around the world. So, the next time you see a big national poll, there's a really good chance this powerful idea is working hard behind the scenes.